Good afternoon, and thank you for joining us on our call today. My name is Christina Spearman from Transcat, and I'll be your moderator this afternoon. Our webinar topic is Identifying Energy Waste in Your Plant or Facility. This topic is being presented by Kurt Genie from Fluke. Kurt Genie is a Sales Applications Manager at Fluke Corporation, where he has worked for 22 years. He is a Level 1 thermographer and Level 1 vibration specialist with 38 years in the test equipment market. Kurt has fundamental expertise in electrical, electronic, mechanical, process, and thermal applications. His work focuses on customer application support and product training in industrial, commercial, utility, municipal, and field service markets. We expect today's presentation to last roughly 45 minutes, and then we'll answer any questions that have been submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Kurt.
Thank you, Stephanie. Good afternoon, everybody. Appreciate your time here today. Again, my name is Kurt Genie with Fluke Corporation. So we're here obviously to talk about how do we find waste in your plant or your building, and the different energy measurement principles that we'd use to do this, and what tools that Fluke offers would allow you to do this. So there's me. You don't need to look at the picture too long. Figure out I've been doing this for a long time. So we'll jump off that screen and go to the next one. So a couple of questions, things you want to think about. How much is your electric bill per month on average? Some of the larger scale industrial plants, it could be several $100,000. Are you paying any kind of penalty from the utility, such as a demand charge or power factor penalty charge, which is an efficiency charge by your utility partner? Since you did a lighting upgrade, how much is your electric bill decreased by dollars and or percent? We'll talk about that. And how much is your natural gas or oil bill per month, and does that change much during the year? And these are all the different ways, obviously, people now quantify using energy is based on these bills. We're going to want to dig into this a little bit further to figure out why these bills might be a little bit higher than normal. So the core part of this obviously is the electrical system itself, which as the backbone, right? This is what keeps everything up and running. Everything's got to be properly functioning. Everybody has to be properly installed and maintained. And obviously looking at and verifying the operation of that is key to anybody in terms of energy efficiency in the market today. So starting out with some basics, what's energy? Energy is measured actually in joules, which people actually refer to as watt or wattage or kilowatts. Obviously, the energy is going to produce work, atypically in the form of light, in the form of heat, or in the form of electromechanical motion. And the ideal efficiency we're looking for in that electrical mechanical motion in the motor is 80 to 90%. 65 to 75% of everybody's electric bill in commercial and industrial operations is electrical mechanical efficiency or electrical mechanical motors. We're obviously driving HVAC systems, conveyor systems, motors, pumps, compressors, fans, blowers. Again, those are the big energy hog in any building. So inefficiencies show up in a variety of ways, but one of those is those motors or those devices get hotter. And the increased heat beyond the operating range of the instrument or the piece of machinery decreases the efficiency and energy becomes wasted. So we're going to measure energy in a variety of ways today. First being heat, second being electrical, third is pressure, steam, air, water, and fourth is mechanical force, rotating or centrifugal. Basically, obviously, we're talking about electromechanical loads such as motors and pumps and the like. So starting off, energy waste is manifested in a variety of ways. First and foremost, as we all know, power consumption, power distortion and overheating. So electrical loads are not working properly, and as a function not working properly, there is energy waste. Second, mechanical is excessive vibration or friction, overheating, and excessive sound. So there are indications, physical indications of either heat or sound that are telling us that things are not working properly. And then looking at input and output pressure drops for conditioned air, for compressed air, controlling temperature in the form of steam and or air or fluid. Obviously, there can be waste there as well. So you can see there's a lot to look at, and we're going to dive into that now. So the first part is a little education on the energy side. For those who are not familiar with all the leading indicators, we're going to talk about those. So if you looked at your building as a whole, whether it's a commercial office building or an industrial facility, obviously there's lots of ways that energy gets manifested and used inside the plant or the building. But the biggest ones we want to concentrate on are things like the lighting, the compressed air, the steam systems. And certainly the HVAC, the motors, the drives, and again, all your electromechanical loads are going to use the majority of the building power as far as that's concerned. So we're going to break it into three pieces. We're going to break the three parts of the building apart and look at them as individual loads or individual pieces, and what is the appropriate measurements for those different parts, and what type of tools would be used for looking at those from an energy efficiency or inefficiency standpoint. So we'll start with the electrical system. So on the electrical system itself, you actually have several parts to this that you'd want to look at. But the biggest thing we want to start with is let's look at your bill. How much is your bill per month? Are you paying both on and off peak rates for use? Are you paying any form of demand charge? And we'll talk about demand here in a minute, what that means. And are you possibly paying an energy efficiency charge called power factor? So all these can contribute to a higher bill. And the latter two, power factor and demand, are penalties placed on you as an end user if you fall outside the tolerance levels that the utility has set for you as an end user. So we want to look at all those. So let's start with power. So as you know, today, we not only as individuals in our homes, but also in our businesses, get a kilowatt hour bill from the local utility. So kilowatts, or power if you will, is basically the energy required to do actual work, such as running a motor. The demand piece is the total amount of voltage and current required from the utility at any point in time during that 30-day billing cycle. And utilities do put levels of what demand is allowed, i.e., here's the highest you can go, Mr. Customer, and let's say it's 1 gigawatt. And if you go over that, there's going to be a penalty. Power factor is really an efficiency piece. And for those who have recently shopped for an appliance like a washer or a dryer or a refrigerator, you'll notice this EER rating tag hanging on there from the Department of Energy. Well, that is actual power factor. Power factor is efficiency. And the easiest way to calculate it is by taking the kilowatts you use over the kVA of the transformer that you have available, and divide kilowatts or divided by kVA comes with power factor. 0.9 or 0.95 is considered efficient. Below, let's say 0.9, even though we show 0.95, is considered inefficient. And I can find more efficient devices to replace inefficient devices and have them pay for themselves based on energy savings, just like lighting. And then last is harmonics and unbalance. So these are two issues within an electrical system, harmonics being form of electrical noise or waste, and unbalance where my voltages on all three phases and or my currents on all three phases are not balanced, they're not equal. It can cause inefficient use of power and cause waste. So we want to have the ability to go out and measure those devices, and the tool sitting up in the top right-hand corner is an example of a three-phase power analyzer called the 435. We have a wide array of these that can do this stuff. And give me these answers. So we would actually log or record data over time. And the idea here is we want to look at usage over time, because there's a rhythm or a cadence in terms of usage in every plant or every building. And you'll have peak times, let's say during manufacturing hours, between 8 o'clock in the morning and 5 o'clock in the evening. And then you'll have off-peak hours after 5 o'clock, where I might still be running production, but my usage starts to drop because not all the machinery is running, and maybe even less on the weekends. So if we start to get a rhythm or a profile, we can figure out how much usage we're using at different times of the day and what types of loads are on during those times. So to that point, we want to go look at major loads. So we could literally move a piece of equipment like this around from point to point, starting at the main service entrance and working our way out to the various loads to determine who's using all this energy. I get the big bill at the end of the month, but I have no idea who's using it. So what if we could start to quantify individual loads? What if we could actually see what loads are efficient, what loads are not efficient? And again, they might be subject for change. Again, just like lighting. So the main things we'd start would be right at the point of connection, what they call the point of common coupling between you and the local utility. So for most folks, that's the secondary side of the transformer that you're hooked to the utility with. To look at total usage, power factor, unbalance, and harmonics. And then we want to start looking at a variety of other things as we move downstream from there, including things along the lines of temperature. How hot is that panel? How hot is that load? So with that in mind, we'd use non-contact thermometers, visual thermometers, or what are called thermal imagers. So the thermal imager, as you can see on the screen there, this is actually a visual thermometer. It's a mini version of it, if you will. Will allow me to see both the heat content, and some of them will also show you a visible image, and allow me to see those at the same time as kind of illustrated at the bottom corner of the screen. But it gets to the question is, why is it hot, right? Reading something with a thermal imager, which is a great tool, will tell me that it's hot, but it won't tell me why. So we want to look at and investigate other methods of measuring these, either with a voltmeter and or clamp on, but potentially in many instances, I'd like to use a three-phase power analyzer to look across all three phases to figure out why is it hot. And then we start to uncover problems like they're unbalanced. The voltages and the currents on each phase are not the same. And if they're more than 10% unbalanced, you're going to have some problems within your plant because a lot of the loads and devices will not like that, not work very well. Looking at harmonic content, harmonics create heat. So ambient on the neutral. And excessive amount of current draw obviously is going to cause a conductor to heat up, very similar to what we have in the picture in the bottom of the screen. Loose and dirty corroded connections, wiring mistakes, not that that ever happens. There's a variety of things where things can be problematic and show up as a function of heat. This is kind of what this would look like. So if I had a thermal imager in my hand, I had the cabinet door open. The connection in the center here, where it says loose connection, that could be loose, dirty, corroded, right there at the top of that fuse clip. And I can see that with the thermal imager. And how we would actually measure that is take a Fluke voltmeter and measure from the top of the circuit to the bottom and actually confirm, based on the voltage drop, that it's a highly resistive connection, i.e. it needs to be fixed on my next maintenance shutdown. If it's hot all the way through the conductor, it will be hot right across the side of this, like we have at the far end of that picture all the way to the right. And I'd use Fluke clamp meter to figure out the overheating is caused by excessive amount of current and how much current is actually flowing through there. And I would compare that to other similar circuits that are nearby to see how much is overloaded. If we are able to measure these things and able to quantify these things, then we can go fix these things, right? Again, the go-to-market phrase at Fluke is you can't fix what you can't measure. So a thermal imager is a great tool because I can document, I can store images, I can share those images with other folks, and I can create reports. And we offer a wide array of these tools, depending on your need and your budget, to be able to fit the need to be able to document the problems you're using. These are also used many times for doing what we call thermal scans inside of a building, looking over heated connections at the bequest of your insurance company. They might be asking you to send them an annual report because they don't want to have fire running through the walls of your building, and so they're going to have you either do it yourself or have a contractor do it for you. So we would go out and follow up with the thermal with the electrical measurements. And this is where, again, we would take a portable power analyzer, move it around from panel to panel, place to place, and look for basically energy waste. Particularly those places that are hotter would be good places to start. So if it's overheated by more than 10 degrees above the nameplate rating on a transformer or a motor, there's a good likelihood that that load is actually going into a failure mode. And so the hotter it gets, the faster it's going to die. And then we can use a thermal imager to detect a future failure, and it becomes a very valuable tool to you as well. One of the things we are very big on Fluke now is wireless tools. So not only a thermal imager is wireless, a power analyzer is wireless, but just a regular voltmeter and clamp on. And we're very concerned about customer safety. So when I'm opening up a live panel to do these measurements, I'm going to have to be in what's called PPE gear. And the longer that panel door is open, the longer I have to stand there in that protective gear, which is not the easiest thing in the world to work with. 2 layers of gloves is tough to document anything with. And it's hot and heavy. So what if we could put the device inside the panel door, close the door, take off at least a portion of the PPE gear, and pull out a wireless device like a wireless meter or a handheld device like a wireless phone or an iPad or even my laptop, and go talk to these devices wirelessly through the panel door. And that's what we call Fluke Connect. So Fluke Connect is a wireless app. It's iPhone, it's Droid smartphone, it is iPad, and we also have a desktop or laptop application where you can go talk to these tools as well and get outside the arc flash zone and be able to communicate with those devices that are inside the panel, or do it at some distance away and create a safety factor for myself. So a 3-phase power analyzer is one of those tools. We kind of talked about that. And this is, again, I would be hooking up right at the main switch gear and then working my way downstream to go measure individual loads to see where the inefficiencies lie. We're going to look at all the 3 phases of voltages and all 3 phases of currents simultaneously, so that we can actually figure out and take a look at the power consumption piece. So typical display off a power analyzer, the ability to see not only the voltage and the current like you would off a voltmeter or clamp on, but additionally now I can see actual true kilowatts, kVA, kVARs, power factor, and actually it's a portable kilowatt hour meter, so I can totalize energy over time and see who's using what, and have it on a circuit for, let's say, for a week, and then know that that individual circuit, that individual load over the course of the week used X amount of power. If that's a constant load, we'll just multiply that up by a factor of 52 weeks, and I can actually figure out how much an individual load is using on an annual basis. So the peak demand piece that we talked about earlier really comes into play, and every 15-minute interval, the utility is out giving you a snapshot of how much you're using. And if they establish a number, and let's say it's, we use again 1 gigawatt worth of power a month, and you use 1.1 gigawatt worth of power at one point in time during that month, they will hit you with what's called a peak demand charge. And that will actually apply for the rest of the billing cycle. So it only takes a one-time occurrence to go above the demand, and now I've got myself another 5 to 10% penalty charge on top of my normal bill. If my bill is $100,000 or more, I think it starts to get pretty costly, particularly if I'm getting that demand charge hit with me every month with the utility. So we can figure out what's using that large scale amount of power and possibly put it on another device like a soft start or a VFD, variable frequency drive, to reduce that inrush current that actually is driving up the peak demand. And these are all things I'm mentioning that a power analyzer can configure and measure, so you can figure out who is using all this energy. So real quick calculation there showing you what this might look like if you had a power factor charge, which is again an efficiency charge. And if you drop below an acceptable level by the utility, again, we're showing 0.97, which would be 97%. I would argue currently that power factor charge, if it's in effect right now, is probably 0.9 or less. So, but again, 90% efficiency, if you think about it, if there's devices in your plant that are less than that, they can pull down your overall power factor and possibly expose you to a power factor penalty, which again, as you can see, starts to calculate out and create some real dollars and real costs. So many folks use what is called power factor correction. This is a way of installing capacitors on the electrical system to be able to compensate for a system that's very inductive and make it more capacitive and bring it back to a closer, what we call unity power factor, which is the equivalent of being 100%. Honestly, the only thing that's ever really been 100% in the last number of years is the incandescent light bulbs. But of course, we just threw all those away. Those are no good anymore. So we've replaced them now with electronic loads. Unfortunately, that the new electronic lighting, such as CFLs or LEDs, or electronic lighting controls, can actually produce a lower power factor now. So we want to quantify. We want to go measure. We want to go look and see what individual loads are using. And then based on that, I can come up with a game plan where I can go investigate a more efficient device and replace the older one that's less efficient with the newer one that is more efficient, and have it pay for itself based on energy savings. And this is a lot how you can use a power meter. So voltage unbalance is almost what it sounds like. Voltage and current are not the same in all three phases, and as a result of that, that load is not going to run very well. So many of the power analyzers do have the ability to running actually what's called an unbalanced calculation, both on voltage as well as on current. The rule of thumb is you'd want to be probably 5% or less unbalanced across a regular load. Greater than 10% voltage or current unbalance is going to be problematic. For those folks in the audience who are using variable frequency drives, that unbalance cannot be more than 2 to 3% on a voltage. So VFDs cannot compensate for unbalanced voltage, and as a result of that, unfortunately, we'll drop a voltage out to one or more phases to the motor, and the motor will pull more current, and the drive will trip. And we will all blame the drive, but the reality of it is it was not balanced going into the drive to begin with, and the drive could not compensate for that. So how do I know why the drive is tripping? We can use these types of tools to help figure that out as well. Harmonics are multiples of the fundamental frequency here in the United States. The first harmonic is 60 hertz. Your second harmonic is 120 hertz, so 2 times that. Third harmonic 180, so forth and so on, up to the 50th harmonic. So 50 times 60, we're looking at about 3 kilohertz worth of bandwidth, or 3,000 hertz. THD, as it's affectionately referred to, is total harmonic distortion, and that's the mathematical equivalent of the first out to the 50th harmonic added together and presented to you as one number. Most people talk about THD when they talk about harmonics, and again, rule of thumb, 5% or less is good, 10% or greater is bad. And you can all see why. We have more current flowing in the neutral. We have overheated motors and transformers, and that's going to decrease the lifespan of those. So you decrease efficiency on electromechanical loads when they get hotter. Harmonics are one of the reasons why these loads get hotter. So we can quantify how high the harmonic content is in the circuit. And there are things like harmonic filter networks and a variety of other electro devices that can reduce harmonic content to help reduce the overall effect that harmonics have on the system as well. But we first need to quantify how bad is it. So one of the things we came up with at Fluke a number of years ago was called an energy loss calculator. We've actually patented this. So what if we could actually put in your effective kilowatt hour rate, your reactive kVARs or wasted energy, what does unbalance cost me, what does distortion or harmonics cost me, what do neutral currents cost me, which is unusable power. Apply your actual kilowatt hour rate as a customer. What do you pay the local utility? We can take this out 3 digits behind the decimal point. So you could say I'm paying 0.0001, which would be 1 cent kilowatt hour. And that, along with the length and the diameter of the cable that's going from the control system or the motor control to the load, I can actually figure out how much IR loss I have and know how much I'm wasting. And we're going to annualize this. We're going to totalize this. So I can run this for a week and basically figure out what is using how much energy, how inefficiently it's using, what it's actually costing me on a weekly basis. And then again, if we multiply it by 52, voila, we've just figured out how much they cost me to run that individual load per year. So now I can put a dollar figure around this and really start shopping for a new higher efficiency device. So we do what's called power quality. Power quality really gets into a whole nother thing, and that is the quality of the voltage on the line. That's what power quality is about. And what is the impact to my bottom line? If I have interrupted service or have unstable voltage coming into my facility or my plant, what disruptions could that costly cost me, including premature failure in my equipment, downtime, loss of production, loss of revenue, a variety of things. So the quantity piece and the quality piece are actually being done at the same time in these power analyzers. Majority of them, if not all, will do some form of this, but actually allow you to do both quality measurements and quantity measurements at the same time while I'm doing my surveys. And we want to, again, move around the plant. So branch circuits, distribution, looking at electromechanical loads off the feeder circuits, figure out who's using all this energy. Give you kind of a flavor for the electrical side. Now we're going to talk a little bit more about the mechanical piece and the process piece. So as we move from electrical distribution and go over to the building infrastructure side, looking at the HVAC system, looking at building envelope, looking at lighting, and we start to get a sense of, okay, how can we go look at these? So the first part of this would be, again, I'm going to still use a power analyzer. I'm going to look at log power consumption on something like a lighting circuit. Now, lighting circuits obviously have a variety of pieces to these days, and the big thing is really changing both the lighting controls. So no such thing as just on and off anymore. There's a wide array of lighting controls where it automatically dims, or if there's sunlight coming in through the side of the building, their shades can be changed automatically or closed to reduce the overall radiation effect, and as well as a variety of different lighting illumination pieces, if you will, from CFLs to LEDs to a wide array of things. But what we want to really consider here and keep this in mind, people are under the impression that lighting is a big percent of your electrical bill. It's actually not. 15 to 20% of a typical bill's energy usage is lighting. That's it. If you've taken the time and effort to put new lighting in and you've cut your bill in half, the reality of it is you probably reduced it by less than 10%. A lot of people don't know this because they don't know from a starting standpoint where the lighting bill was to begin with. Because lighting is not called out as an individual load in an electric utility bill, it's part of the load. So I really never knew what it was to begin with, so it's really tough to quantify how much I've reduced it. We can do it on paper, but the reality of it is you have to compare that to your overall bill to really see how much it affected it. So we do sell luminance meters, like a light meter from Ampro. We sell LED light meters to look at luminance levels, and then along with an area measurement to figure out how much lighting I need, and power measurement, I can start to quantify the dollars being spent. So obviously we're using a variety of tools to help quantify a variety of things and ultimately to come up with savings. And lighting does provide savings, make no doubt about it, it absolutely does. The argument we would have at Fluke is it's a much smaller percent of your overall bill. So if we could find inefficiencies on the electromechanical side of the house, the big motors, the big pumps, the big compressors, the big fans, and replace those with higher efficiency devices, just like lighting, we could have an even bigger impact on your bill. Okay. HVAC. So we all have HVAC systems in the plant. We're moving air around. We're trying to maintain indoor air quality standards under the ASHRAE standards for proper temperature and relative humidity and airflow to keep this a good, safe working environment, whether it's a manufacturing plant floor or an office building. And obviously there's a variety of different loads and things that are on that system to be able to make that happen. So if we look at from the standpoint, where are the possible savings on the ventilation side? Well, recalibrating my thermostats or verifying them against a known accuracy of outside thermometer or reference thermometer, I should say. Optimizing ventilation. So this is a lot where people would use things like variable frequency drives to create the certain amount of airflow through the building. But we don't want to have too many turns of airflow because then I'm taking conditioned air and I'm blowing it out the ceiling of the building. So we want to right size the fans, right size the motors, right size the air turns, and play that against the electrical demand so that we can reduce overall consumption by doing this the proper way. And again, we'd want to go out and measure all these. So looking at things like outside air, looking at airflow, looking at power, looking at temperature vibration, looking at pressure drops or leaks, air leaks, we can start to quantify where the losses are and what am I using versus what am I wasting in an HVAC system. So the first part, just like everything else, let's go quantify the power piece. Let's go look at the HVAC panel and let's go monitor load over at least a week's worth of time, get an idea how much am I using. And again, how much am I wasting? Am I paying a peak demand charge as a function of that big compressor or pump turning on and driving up my electric bill? And how hot is everything? Is everything inside the operating limits of where it's supposed to be? So with that, at Fluke, we use a variety of tools. We don't really have a one-box solution. Nobody does to do all these things. So these tools all have their own expertise. A power logger is, as it sounds, looks like power recording over time. A thermal imager is for the hot spots, if you will. We have a unique piece that's launched here in the last 2 years called a sonic imager. So this is an ultrasonic leak detector that can see leaks of any type of typical gas or compressed air or steam leaks upwards of 150 feet away or further. And things like an 810 vibration tester to see the mechanical health of everything that rotates these days, like motors, pumps, compressors, fans, and blowers. So logical, right? Let's see how much it's using. Let's see how much temperature this chiller is creating. How much vibration is in the primary pump? What's the pressure drop on that line, whether it's fluid or air? And let's also measure the temperature of that. So you can see we would move around from point to point and make a wide array of measurements. And we use a chiller as a typical example. So doing vibration measurements, doing thermal scans on it, looking at power usage, harmonics, and unbalance. And we have high accuracy pressure gauges and calibration gauges to certify and calibrate the temperature and pressure indications in sensors and transmitters that might be hooked up to these types of devices to ensure I'm getting accurate readings going back to the control system. So again, a chiller is a typical one, right? We're going to create chilled water. Chilled water can help create air conditioning, but it could also be used for a variety of other purposes in the plant. You know, how much power consumption are we using? If we could reduce the power consumption by fine-tuning this, if we could, you know, use cleaning salts, corrosion inhibitors, if we could occasionally shut down a secondary pump, there are ways we can start to figure out where the wastes are, where the savings could be had based on making some changes on this chiller system. But again, I have to measure it. We have to quantify it first. Same thing on the heating. So steam loss, right? We are going to fire a boiler up using either oil or natural gas or some other kind of fuel to create process steam. We're going to regulate that. We're going to run that through our system with a pump. We're going to put it out through steam traps to regulate, to control that steam flow as it goes through the building or the plant. We need to make sure all is working properly. So again, we'll start out with the obvious. Let's go look at temperature. Where do we have cracks around the refractory of the boiler or the furnace? Where are we losing energy? Where are there lines that are not properly insulated? We can certainly see all that with the thermal imager. So where do I have air leakage? So lots of places we can go measure, right? The whole idea of this whole presentation, and you guys are all getting a copy of this, is let's give you a starting platform to think about where could I go use the equipment and what kind of things I could go find and what kind of waste I could use this to help create a more efficient environment in terms of energy waste within my building. So steam traps is a big one for those using steam. Traditionally, I don't have just a couple traps. I might have dozens or hundreds of these in my plant or my facility. You go to places like New York City, Con Ed, actually the utility there operates the largest steam system in the world with 1,000 miles of steam lines running all around underneath all the buildings in Manhattan and other parts of the 5 boroughs. That steam comes up through the building, and a lot of the commercial office buildings are using that steam for heating the building. So if I've got a lot of traps that are not working properly, and a trap should have a very distinct hot and cold side to it, but if it's not, if it's bleeding through, as we call it, you can lose hundreds of dollars a day in lost energy. And for every trap I find that's not working, replace a proper one, I'm going to save lots of money. So steam waste is a big one. Or wasting energy that created the steam, and the steam trap itself is not working properly. So I don't have good steam control. Building infrastructure, for those who may recall, many years ago, I think through the Obama administration, there was a weatherization program going on where people were trying to look for loss of insulation around the windows of the doors, the water coming in from the roof, and there's a big push in the marketplace. There was billions of dollars being spent on this to tighten up the envelope, the energy envelope of a home or a building. And again, using something like a thermal imager, we can detect where these losses are. This is kind of what this would look like. So you can even find the leak on the roof. So we can find the origin of the leak. Where is the water contained inside of my roof under the substrates of the roof, and where is it leaking from? To just fix that part of the roof. We don't have to do the whole roof, just the part that's leaking. And we can certainly see that and mark that out with a paint gun with the use of a thermal imager, and this is typically done at dusk or at dawn when the sun's out of the sky, and the part of the roof that's dry will drop in temperature, and the part that's hot, the heat that's buried underneath the surface of that roof will rise to the surface as a heat pattern, and I can see where the trapped moisture is with the use of a thermal imager. Very useful tool. Last but not least, the production piece is where we want to talk about. So how much energy is being used by the mechanical loads on the production side of the house? How much am I using in terms of compressed air to regulate those loads, or use with things like pneumatic tools? So again, we'd start with power. We always want to start with power. How much energy am I consuming? And go look at the primary motor control centers, but then work down to individual panels and use different versions of power analyzers. Here's two listed here. There's a 173638 at the bottom of the screen, and a 435 or 438 at the top of the screen. Different versions, but does similar things to be able to quantify, again, where is all that waste? Who's using all this power? And record it over time. So we want to look at a cadence or usage of power. When's my peak demand time? What loads are on or off during that time? What things are cycling on and off, like a compressor, for example? And where could I possibly install things like a soft start or a VFD to reduce the overall, what we refer to as inrush current or startup current, which is peak. So a motor or a compressor or a fan or a blower, if I do not have it on a soft start or a VFD, will draw anywhere from 2 to 10 times normal running currents for a very short amount of time. And that peak current will actually drive up your demand. So can we find a candidate that we are seeing it's doing that, and replace that startup with either a soft start or a VFD to make that situation reduce or go away? So again, looking at peak demand based on things cycling on and off. In electromechanical loads, lots of things we can go look at. Obviously, not just the power quality feeding the load, is the quality of the voltage good enough to support the load? Well, what's the operating temperature of the device? What's the actual health of the insulation, which we would do with something like an insulation tester? How balanced or unbalanced is that load from a standpoint of voltage and current? What's the operating temperature of it compared to the nameplate? What's the vibration of that mechanical load look like? I'll start with the overheating piece. This is a standard NETA standard guideline. For every 10 degrees C rise above nameplate, so let's say the nameplate on a motor is 40 degrees Celsius, and I now see 50 degrees Celsius on the display of my thermal imager, you can lose half the life of the insulation of the motor. This, by the way, also applies to things like transformers. But again, could be a pump, could be a fan, could be a blower, could be any number of things, but the motor is going to be the heart of this. And as you can see, for every 10 degrees Celsius rise beyond that, the life of that device drops dramatically, doesn't it? So it'll overheat, and insulation will fail, and it can fault any one of the 3 phases together and any phase to ground. So I really have 6 fault paths on a motor. If it gets hot enough, the insulation gets brittled, it cracks, and it faults, and it dies. So, why is it hot? Well, I don't have proper airflow across the cooling fins. It's not being properly lubricated. It's out of alignment. There's electrical unbalance. So the motor's drawing excessive amount of current on one of the 3 phases, and as a result of that, it's getting hot. So again, we're going to use the temperature piece as an indication of a future failure, but go measure with other tools to figure out the why. So again, we've talked about this already. Thermal imager, great tool. Certainly any number of choices we have to fit any size application or budget, depending on what you're trying to do. A model called an 810 or an 805. These are little handheld vibration testers. These can actually quantify the level of vibration on a 1 to 100 severity scale. Where is it on the motor drivetrain? So we would test it at the non-driven end of the motor, the driven end of the motor, go across the coupling, the driven end of the pump, the non-driven end of the pump, or the compressor or the fan, and measure vibration on each one of those points. And the analyzer at the end of this will tell us the level of vibration and where we are in the scheme of things in terms of how bad is it. Obviously, green being good and red being bad. So this is kind of, think about it being years, months, weeks, and days worth of time, and what I need to do about it. And that all happens in anywhere from under a minute to upwards of 10 minutes, depending on the complexity of that motor drivetrain. So we have numerous examples of where and how these devices will pay for themselves, what we call case studies on the Fluke website. So I can find a lot of problems with the vibration tester. Right? And if things are mechanically unstable because of a bearing problem, because of looseness, because of misalignment, because of unbalance, then the health of that mechanically is going to go down quickly. And if that big motor, pump, or fan or compressor dies, what's the impact to my HVAC system? What's the impact to my production line when that goes down for every hour that it's down? So this is a tool to be able to trend the data over time, to track it as a database, and to be able to create reports. Compressed air is a big one. We're getting to the end of this. And what that would basically entail is the idea. I want to look for pressure drops or losses. So the primary source of those leaks, hoses, connections, valves, cylinders, drainage, anywhere where I'm dropping pressure is going to cause that compressor to run constantly. So three things are kind of happening at the same time. I'm using a lot of energy, wasting a lot of energy because the compressor keeps cycling on and off. I've got pressure drops that are out on my production line or my pneumatic controls, so my process does not work properly. I'm literally running my compressor to death because we only have so many run hours on the compressor, and when you run it out, then now you've got a capital expenditure on your hands, $50,000 or higher. That's going to basically cost you a lot of money to replace. So where's the inefficiencies? So we use a lot of power with compressors. Compressors as a category use all, excuse me, I apologize, 10% of all electricity here is used in the United States. So that's a big number, right? So where are compressors used? Think about it. Compressed air, also refrigeration, right? How much refrigeration do we have in the States? Quite a bit. But when the compressor goes down, or as the compressed air level drops, what's the impact to the customer who's using that compressed air? So we've launched a device a couple of years ago called an II900. There's now a model called an II910. These two devices are basically used for one purpose in life, and that is to find where those leaks are. So that could be compressed air, that could be steam, that could be argon, that could be nitrogen, that could be hydrogen, that could be helium, that could be any number of types of gases. And so this is looking at pressure changes with 64 sensors that are wrapped around a camera. We have the ability to scan very large areas for leaks and quantify where they are visually. I don't have to know what they sound like. I don't have to put headphones on. I can visually see them, so I can identify where they are and are they a real leak or not. And how we do that is if we move and the leak moves, it's a reflection, which I can't pick up with headphones. But if it's a real leak, it stays put when I move, and we can quantify and tag it, fix it, then shoot it again and know that the leak went away. So what if we could look at before and after? And we did this with a company called Genie up in Washington State near Fluke. And we did a before and after on 4 compressors they had running constantly. And basically they make lift trucks. So in the course of lift truck, how do I put that together? Well, I'm using a lot of pneumatic tools with a lot of compressed air, right, to put their own product together. And I could look at the before and after. So that's exactly what we did. So we went out and did a whole series of power measurements on all these compressors. And then after we found all the leaks, ran it again, and here's the good news. They were able to idle the number 4 compressor, which is actually the largest user of electricity, and they recovered 25% of their lost capacity in terms of air with, as you can see, huge savings, almost $50,000 worth. So the whole idea of that is, hey, these compressed air leaks, or leaks in general, are costing me money. I'm paying for a gas that I'm not using because it's leaking out into the atmosphere. And what if we could fix those? So I've come to the end of the point. I'll have to apologize to Christina. Ran 5 minutes over. Sorry about that, Christina. Hopefully you all got something out of this. We feel it's a pretty comprehensive way of looking at energy savings and usage in a plant. Would love to have an opportunity to have a conversation with any of you folks directly through Transcat, and would certainly welcome the opportunity to come on site to a facility to demonstrate any of these devices, or have a one-on-one conversation as an online meeting like we just did here today, but on a specific product or application that you have in mind. So thanks for the time. Thanks for the opportunity. Thank you, Christina, for having and hosting us here today. And with that, I don't know if we had any questions.
Yeah, thanks. So that concludes our presentation portion of the webinar. We'll now move into the question and answer session. Just as a reminder, if you would like to ask a question, please send it through the question box in your webinar controls. Let's move on to the first one. How much wasted energy comes from a defective steam trap per day?
Well, on average, how much energy gets wasted is probably the better way to phrase that one. Probably minimally $200. It might be more, depending on the amount of pressure on the line and the stream regulation. But let's put it at several $100s a day. And again, people using dozens and or hundreds of steam traps, so it's not unusual for customers to walk around and just at a day's time find 5 or 6 traps that are not working effectively. So if I do this as a full-time job and really start looking at everything, you'd be amazed how many you're going to find that have are non-functioning and wasting energy over time.
All right, thanks, Kurt. Let's go on to the next question. What Fluke product would have the biggest impact of finding energy waste?
Well, frankly, right now the sonic imager is probably the #1 tool we're seeing, just because of the fact that compressed gases and compressed air is the biggest single user of energy, compressors, I should say. So if I can reduce leaks, I can reduce runtime, it's going to reduce energy usage. So that last illustration we used for the lift truck manufacturer is a perfect example of what we're seeing. So we use a combination of a power analyzer and an ultrasonic leak detector to actually be able to quantify that dollar number to show real energy savings.
Okay, thanks. What product would I use to find electrical waste?
So that's obviously, I think we illustrated multiple times over as a power analyzer. Something along the lines of a 1738 or a 435 series type product has a full set of suite of capabilities to find these things and quantify. And again, put a dollar figure on it. That's the biggest thing. So we can actually put in your kilowatt hour rate, and we totalize energy, we'll totalize dollars as well. So you can see how much energy and how much money an individual load is using within your plant.
Okay, looks like those are all the questions we have for today. So that's our time. If you have any further questions or would like to find out more about Transcat's product and service offerings, please contact us at 800-828-1470 or on the web at transcat.com. I just wanted to mention again that each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. Thank you for joining us. Have a great day, everyone. Thank you, Kurt.
All right, thank you.
All right, thank you.